Hello, my name is Andrew Greiner and this is Lab 4. The objective of this lab is to analyze and model the motion of a spring mass system which falls from rest at an arc. As a result of this lab, the motion was successfully modeled by use of the computational model. In this video, I'll present an introduction, the physics principles used in the lab, the presentation of the computational model, a comparison of the observed and predicted motion, and I will answer the what does it mean questions. The main physics principles used in this lab were Newton's second law and the energy principle. Newton's second law is used in situations where F net is not equal to 0. It also updates the velocity of the system. This is used in our code by updating the velocity of the ball. The energy principle is that the total change in energy of the system is equal to the sum of all energy changes taking place in the system. Here, the energy changes are taking place in kinetic energy, potential gravitational energy, and potential spring energy. And the three equations that relate to those three energies are shown here. The forces that come into play in F net are the gravitational force and the spring force. The oscillation period equation was also used to calculate the spring constant and is shown at the bottom of the screen. Here are the important bits of code from the first half of the computational model. In here, we set our system properties and initial conditions, such as the mass of the system, the initial position of the system, the initial velocity of the system, and the initial time. In this other initialization category, or section, the delta t time step is set, which matches the frame rate of the video. Gravitational constant is set. The spring constant is set, which was found by manipulating the oscillation period equation. The last length of the spring is set here, which was found by manipulating the spring force equation. And the length of the spring is set, the direction of the spring relative to the axis is set, and the difference between the relaxed length of the spring and the length of the spring is set. And in here, this is where the initial energies of the system is set, which are the kinetic energy, potential gravitational energy, and potential spring energy, which correlate to the equations which I mentioned in the previous slide. Here's the important code from the second half of my computational model. In this section here, the forces in each run of the loop are calculated. Since the only forces acting upon the system are the force of gravity and the force of the spring, those are the only two we have to worry about. The force of gravity is calculated by use of the force of gravity equation in the y direction shown here, and the force of the spring is calculated here by use of the spring force equation. This line of code here represents Newton's second law and updates the velocity of the system, and the one below it updates the position of the system. In this section, the data relative to the length of the spring is updated each time the loop runs. And in here, the energies of the system are updated as well. This graph represents a comparison between the observed and predicted motion of the spring mass system. The blue line represents the motion of the model data, and the red line represents the motion of the observed data from tracker. As you can see, the two lines start out very close in the beginning, but the model data seems to get ahead of the observed data as time goes on. This is likely because in the computational model, we do not account for the friction forces that are present in the tracker video. This will cause the modeled motion to get ahead of the actual motion. Also, there might be some motion in the z-axis that we are not accounting for. The first what does it mean question asks if the energy principle is satisfied in the model system. And the answer to this question is yes. In this situation, the energy principle states that since there are no outside forces acting upon the system, the total change in energy would be 0. And in this graph resulting from the computational model, the yellow line represents the total changes in energy, which is always 0. So yes, the energy principle is satisfied. The second what does it mean question asks us to compare the oscillation periods using x position and y position data. After calculating the oscillation periods using my x position data and my y position data, I found that both oscillation periods were somewhat equal. This is predictable because the time it takes for the system to return to its original x position and the time it takes for it to return to its original y position should be the same on every oscillation.